Today, we're looking at curve fitting in Python, and curve fitting has a very particular purpose. Suppose you go out in the field and you measure some X data and Y data that you can make a scatter plot out of. This data likely depends on physical parameters. For example, if you're measuring an object falling, this depends on the gravitational constant. It also depends on the initial velocity of the system as well. The purpose of curve fitting is to look at the data and extract these physical parameters. What is gravity? What was the initial velocity of the object as it was falling? In this video, we'll explore specifically scipy's function curve fit. And it's not always easy to do. You have to give good initial guesses, and you got to make sure your data is standardized. Please be sure to like and subscribe. There'll be more videos like this in the future. Join the Discord server. There's a link in the description to that, and enjoy. So for curve fitting today, we just got NumPy, Matplotlib, and pandas. We're just going to open up a little bit of data. The main function, of course, is from the scipy.optimize library. We're looking at curve fit. And before we get into lots of examples and stuff, I think it's really important to understand what the purpose of curve fitting is, because there's a difference. In my last video, I looked at interpolation of data, and curve fitting is slightly different, and it's got a different purpose to it. And so with curve fitting, you're given X data and Y data, sort of like interpolation as well. But here you have a model function f. This is a function that beforehand you think models your data properly. It could be a parabola, it could be a linear curve, it could be anything, but you have an idea of what the function is beforehand. And that function depends on unknown parameters beta. Beta is a vector here. It contains multiple quantities. So if your model is ax squared plus bx plus c, that's what you think your data follows, that sort of curve, then beta contains a, b, and c of that curve. Those are the model parameters. And then y and x are like the data, and that sort of tells you how your data goes. And so the goal of curve fitting is to find the best set of parameters beta, again, parabola, the best values of a, b, and c, if you're talking about a quadratic curve, such that the function y equals f of x beta, if you plot that line next to your data points, it best resembles the data. And best resembles I have in italic here because it's sort of ambiguous what that means. Now, one way of doing this is to minimize the sum of the squares. So f of xi beta minus yi. So this is, I plug in my xi data point. So if that's a parabola, I go to x, I plug in the value, I get a function there. So that's my model. This is the guess that my model is for a particular value of beta, or values of beta, because remember beta has multiple things in it. It's a vector. And yi is this data point. So I look at the difference between those, I square it, and I sum these all together. And of course, if there's a difference between those two data points, then this is large. And if this is equal to 0, then all the model fits the data points perfectly. So this is summing over all the data points. Now you minimize this. You can't change your data points, xi and yi, because those are fit. Those are set. You collected those in the field. But you can adjust the parameters in beta. So you need to adjust beta such that this function is minimized. And so this becomes like an optimization problem in calculus. How do you best find the parameters beta? And xi and y are the data points. So this is called the method of least squares. And what scipy.optimize does is it has a way of getting the best values of beta. When it gets to really complicated functions, eventually this leads into things like machine learning and other things as well, but we're keeping it simple for now. Now, if the yi data points, you're not always super confident in your data. If they have error on them, then minimizing, this looks exactly the same as above. It's the model minus the data squared, but you also divide by sigma I squared, where this is the data point. So this is all contained in the sum. This gives the maximum likelihood estimate for beta. So if you minimize this function, which itself is a complicated thing to do. That's sort of taken into account by scipy. We don't discuss that here. But given that you can minimize this function, you get a maximum likelihood estimate for beta. What that means is that given your xi and yi data points, this is the most likely value of beta there can be, given the data that you have. So hopefully the purpose of curve fitting is established. We can now look at some basic data. So here's some x data and y data. And I use this convention _data always for variables that are the data that we're looking at in the problem. And we can, of course, scatter plot this. And so I have a function that looks like this, and it kind of looks like a parabola. And so our goal here, getting started, is we're going to fit this function to a parabola. So the model that we have here is, well, beta is ABC, like I said above. So beta is a vector. These are the parameters. And the model, f of x comma beta, which is f of x ABC, because beta just is ABC. These are the parameters of the model. It's good to be thinking like this in terms of model parameters. It's just a times x minus b squared plus c. This is like a form of a parabola. It's written in a particular form, and you'll see why in a little bit below, why I write it in this form. So we want to find the optimal values of a, b, and c that fit this data above. And so there's two steps here. First, we need to define the model function. That's pretty easy to do in Python. We just code this as a function. So f of x and then these other parameters here. And then we use scipy's curvefit function to get the optimal values of a, b, and c. This does it using a pretty complicated algorithm. Again, it's sort of beyond the scope of this video, but it can do it, and it can do it very easily. But what it requires is giving good initial guesses for beta. So we have to guess initial values for a, b, and c. And this isn't always easy to do, and so probably the biggest challenge when it comes to curve fitting is to getting a good initial guess. And I'm going to really focus on that in this video. Because if you have a really complicated model, you have to be very careful with your initial guess, or the algorithm might not run properly. It might fail, you might not get optimal parameters, for example. And so that's something I'm going to focus on, very important. So for the model here, this is our model, a times x minus b squared plus c. I just define a function, model underscore f. In my videos, underscore f always means function. It's something that takes in variables and spits out variables. So it takes in x, and it takes in the model parameters a, b, and c, and it returns just this thing here. So again, what we're focusing on is getting the best values of a, b, and c to fit this data here. So here's my model function. And using scipy curvefit is very easy to do. Again, the focus of this video isn't so much to learn how to do it, because there's many online tutorials on, here's a one line of code of how to do it, but more so everything else that comes along with this. And you'll see in my examples further in the video that it's not always so easy to do this. And so here's my model function. That's the function I'm trying to get. I give it my x data and my y data, and I give it an initial guess here. So you'll notice that the order is A, B, C, and I give 3, 2, negative 16. And you might think, where the heck did you get those guesses from? Well, starting with C, right? C is the value at the minimum of this function. When x equals b, the value of this function is c. So the minimum of here is right here, approximately. So you can see when x is about equal to 2, I would guess that's where the minimum is for this function. The value of this is around minus 16. So that's why I guessed 2 and minus 16 for initial guesses for B and C, and they come second and third. 3, which is the initial guess for A, well, A like scales how fast the parabola goes up. And I can see that as it goes 1 over from 2 to 1 here, it goes approximately from negative 16 to negative 13. Again, the guess doesn't have to be perfect, but I think it's a pretty good guess for what that is there. So I give it my initial guesses, and I get 2 things here that are returned. So I sort of go like this. It returns a tuple, and I just extract those 2 things. So pop t, these are like p, or rather I call it that, but it's really p optimal, the optimal parameters. It gives the optimal parameters for model f, and this has 3 parameters. So if I look at pop t here, it has 3 things, and these are the optimal values for a, b, and c. So that tells me what a, b, and c, should be in this function. So curvefit returned. Now a little bit more complicated is p covariance. This is the covariance matrix of the parameters. And you can use it to get an estimate of the error on the parameters. And I'll go into that in a little bit because it's a little bit complicated. But it's based on how sensitive the goodness of fit is to changing those parameters. So you have your function, right? Your model function, and you say, well, what happens if I change a little bit? And maybe it doesn't do a whole lot to help with minimizing the least squares. And so then there's more error on the parameter because it's saying, well, I can adjust it like this, and it's not doing a whole lot. And so that sort of is how you determine the error on these parameters. For example, if I change a from like 2 to 5 and it's not really doing anything, then I don't really know if a is between 2 to 5, right? So that's sort of that there. But it also gives the covariance between parameters. So for example, if 2 parameters are related, if changing a and changing b do kind of the same thing, then maybe you only need 1 parameter. So maybe those parameters are sort of related in some way. So p covariance is a matrix. So this is related to the error on a, b, and c. And these are the off sort of diagonal elements that tell you how the parameters are related. Anyways, we can plot the function with the optimal parameters next to the data. So I extract my optimal parameters from P optimal. So remember A optimal, B optimal, C optimal. So I get those here and I make some X model. So underscore model is what we get from the model. These are like the optimal parameters, and this is what our model is telling us after we curve fit the data. So that's what underscore model means in this video. So I go from the minimum to the maximum of the data. I just choose 100 points, and then I use the model function, model f, which I defined above. This is the quadratic curve. And I give these parameters here. So I give the X model, and I give A, B, and C optimal. And so that gives me an array of X and Y for the model, and I can plot the data next to the model now. And so here's my X data and Y data points, and here's my X model and Y model. So I get this curve here. But of course, in curve fitting, as you'll see in the future, it's not so much plotting this curve next to the data that's important. It does sort of tell you how good of a fit it is, but what you're really after is A, B, and C, because these tell you something physical about the model, right? Maybe it tells you about the gravitational constant, or it tells you something else. So these parameters are really what you're after when you're doing curve fitting. So, like I said before, the covariance matrix is a little bit hard to interpret, but you can sort of do it as follows. So the error on the parameter, the error on A, right? Because you get an optimal value for A, but what's the error on that? Like, how confident are we that that's the value? So that's related to how sensitive the model is to changing that parameter. So like I said, if I change it between 2 to 5 and the model isn't really doing a whole lot, then it's, we don't really know whether or not A is between 2 to 5. So does changing the parameter slightly, give a better fit? So does it change the result of this minimization function that I want to do? So I'm going to look at an example here, and I think this really helps understand what's going on with this matrix. So here's a fit function, and it's sort of exactly what I did above, except I'm introducing a new parameter d. So I have my quadratic curve, and then I have this d times 0.0001 times cos x. So this is sort of like a term that's really, really small. So I can change d all over the place, and this isn't really going to do much. So it means that there's going to be a lot of error on d because we don't really know what the value it is. D could be 0, which it technically is, but it could also be, all these other values because there's this factor here. So I can get the best fit for A, B, C, and D, and I can look at the covariance matrix now. And you'll see that this value here at the bottom right, which is the variance of the parameter d, is really large. So this is related to the error on d. Everything on the main diagonal is related to the error of the parameter. So if I look at this here, you see that it's 4 by 4. The main diagonal is related to the error on A, B, C, and D. And I've taken the log of the covariance matrix diagonal. And you can see that the error on D is really big. So this parameter has a huge error on it. Furthermore, the covariances across these here are very large as well. That suggests that you only need one or the other of that parameter. And we know that D doesn't really matter at all in this model, so we don't need D. That's essentially what it's telling us. So if you see something like that here, it means that changing that parameter doesn't really have a big effect on the model, so you can usually get rid of it. And so hopefully that helps you understand the covariance matrix of the parameters. So I think it's good to look at 3 quick examples here, and they sort of go into common things that you run into when you're dealing with data in the field. So the number one thing that you'll probably do with curve fit is fitting Gaussian curves, because the mean, mu, and the standard deviation, sigma, tell you a lot about different things. So for example, let's open some data here. So here I have X stuff and Y stuff. This is just some data. And I can make a plot here. And you might be wondering what the heck this is. Well, this is the spectrum of energies. If I take a sample of cesium-137, which is a radioactive substance, and I'm looking at the photon energies from a detector, this is the spectrum of energies here. And this is an arbitrary units here. So this doesn't correspond to any energy. These are just arbitrary. They're like channel numbers in electronics. You can calibrate it so that this tells you the energy, but for now they're just arbitrary. And so the question is, I have this main curve here, and this is the main, what's called the photopeak. These are like the main energies emitted by cesium-137. But it always emits technically a constant energy. There shouldn't be this width here. If this was like you truly knew the energy of the photon, it's always constant. And you can see that there's a width here. What this means is that the detector isn't perfect. The detector has a resolution to it, right? You can't see everything exactly. So if I fit this to a Gaussian, the mean value will tell me what the energy is, And the standard deviation tells me about what the error or the resolution of the detector is. So yeah, the mean value is the peak, right? If I fit a Gaussian and I take the center, on average, it will get the thing correct. And the width is the resolution of the detector. And so the perfect curve for that is a Gaussian curve. And we're going to use mu and sigma to extract information. So you can see that we're using curvefit to get parameters that give interesting information. In this case, mu tells us what the energy is, and sigma tells us about the resolution of the detector. So here's the Gaussian curve here, and I just define it as a function. And what we want is we want to fit only this data here. So we're going to take a subset of the data. And so what I'm going to do is I'm going to take some x data. Now I'm defining data because it's the stuff that we're actually interested in. I only want the values between 725 and 850. So indexing like this tells me take all the data between 725 and 850. So it's really just selecting this peak here. And I do the same thing for the y data. I only want the y values where I'm in between these x values on the curve, right? If you haven't seen indexing like this, I suggest checking out my basic Python tutorial videos, especially NumPy. And so here I get only the x data and the y data that I want, and I have a subregion of the plot. So rather than plotting this whole thing with junk here on the side, which corresponds to other things, I just have this curve here. And I want to fit this data to a Gaussian curve. And of course, I do it exactly as I would before. P optimal, P covariance equals curve fit, right? This returns two values, so I just get them like that. I give it the Gaussian function, the x data and y data, and I have to give it initial parameters. And so here it's pretty simple. So my initial value for A, which is the amplitude of the Gaussian, well, I just look up the top value here, so that's 2000. So that's my initial guess. Mu, which is the center of the Gaussian curve, I give 790 because that's approximately sort of in the middle here. Sigma, I give the value of 60 because if I look sort of like here to here, it's around, I would say, about 60. It's in the same order of magnitude, so I've given it a decent guess. And so I can extract these parameters and I get the optimal parameters. Remember, P optimal parameters is 3. So this gives me my optimal value for A, mu, and sigma. And I extract them here. Same as above, I give X model and Y model by doing many points in the X data range. Then I give my Gaussian function, my X model, and my optimal parameters here. So I'm just plugging in the super resolute X array here and all the optimal parameters. And so I can get that, and then I can plot X data and Y data next to the model. And you can see that the model does a pretty good job. And again, the point isn't necessarily to look at this curve or do anything with this curve, but rather to look at the optimal parameters here. So mu, which is the energy, is 786, and sigma, which corresponds to the resolution of the detector, is about 58. And I can look at the error on these parameters by looking at the square root of the diagonal. I told you that the diagonal of this thing here represents the error on the parameters. If you take the square root of each of these elements, it gives you an estimate of the error on that parameter. So here I look at the diagonal of P cov. So if I take P covariance here, it's a 4x4 matrix, or 3x3, sorry. And then diagonal just takes these three elements, and then I take the square root of those three elements. And so I find that the error on the amplitude is about 5.7. For mu, it's about 0.14, and on 58, which is sigma, the error is about 0.26. So pretty small errors on these parameters, which is good. Now, suppose there are errors on the data, right? And there will be errors on this data. As it turns out, this is from a counting experiment. And whenever you have a counting experiment, the error on these data points is equal to the square root of the height. That's a statistical fact. And it has to do with the fact that the distribution in each bin is Poisson. So the errors, delta yi is the ith data point, is equal to the square root of yi. So these are the, like I said, the true errors of this counting experiment. So here I get my y error data. And I can plot the data with the error bars on it, like this. So here I'm looking at y error data. And you can see that the error bars are slightly larger up here than they are down here. So we can get the maximum likelihood estimate for A, mu, and sigma using curve fit. I just have to give this additional argument, sigma is equal to y error data. I give the same initial guesses, and I can get my optimal parameters. And you can see that they differ ever so slightly from above here. Here it's 786.33, and this is 786.29. So pretty close. Doesn't make a huge difference in this question, but especially when you're dealing with small data in counting experiments or other things like that, it's really important to use the sigma argument to get the maximum likelihood estimator. Something worth noting is that if all the errors are the same, if sigma yi is constant, these are the errors on the data points. If I go up to this formula here, if I'm optimizing this function where all the sigma i's, these are the errors, are the same, I can just pull this outside of the sum, and it's the same thing as least squares. So if the error on every data point is the same, you may as well just do a least squares fit. But here, of course, the errors aren't the same. The errors up here are larger than the errors down here. So here's a final example, and it has to do with standardizing units, which is really important when you're doing curve fit, and really important especially if you go on to things like machine learning. Standardization is super important. So this is the Leonard-Weibeck potential. It gives the potential between two atoms, and it sort of is constant like this. It drops down, and then it goes up. And what that means is that atoms in this particular region are attracted to each other. It goes to 0, there's nothing, and then they're repelled from each other. So I'll show you what that looks like. So I opened some data, R data and V data. And so here's my V of R, my potential, and here's R. And when V is negative, the potential is negative, they're basically attracted to each other. Here it's approximately around 0, and then it goes up and up and up really high. So that means that they repel each other. And we want to fit this here to this curve here. And we need good guesses for epsilon and sigma. But you can see that the units in standard units in joules and meters, this is 1 times 10 to the negative 9, and this is 1 times 10 to the negative 21. So we're going to normalize our data first before we get into any curve fitting, and that will help scipy's curve fit function. So what we'll do is we'll multiply the x-axis by 1 times 10 to the 9. This converts everything with dimensions of meters to nanometers. So, things will be standardized. It'll be close to the order of magnitude of 1. I will also divide the y-axis by Boltzmann's constant. Kb is equal to this value here. This converts all quantities with joules to Kelvin. So rather than measuring the potential in joules, you measure it in Kelvin. And the units are, closer to order of magnitude of 1 rather than 1 times 10 to the negative 21. And this really helps with the scipy curve fit optimization procedure they use. If you have values this small, it's not really adapted to dealing with data like this. So I change the scale of the data here, and I can plot it again. And you can see that, it's still 300 to 100. So this is fairly big, but it's not super, super small like before. And then here it's just between 0.3 and 1. So this makes it easier for curve fit's optimization procedure. So we want good initial guesses for sigma and epsilon, and I don't think it's obvious just looking at the curve what sigma and epsilon initially will be. So that's when it requires knowing a little bit about your function. So from Wikipedia, you have that the minimum of this function is that r is equal to 2 to the 1/6 times sigma. So that gets me to get sigma. If I look at the minimum here, this value here, sigma is equal to 2 to the negative 1/6 times r. So r is about 0.4 here. So I need to multiply that by 2 to the negative 1/6. That gives me a good initial guess for sigma. So looking at this plot here. And at the minimum, the potential has a value of V of R is equal to negative epsilon. So here I'm at about negative 120. So that tells me that epsilon is equal to 120 approximately. So I define my model function with R and then the parameters sigma and epsilon. And I define the function like it is written above. And I obtain our initial guesses like we got above. So epsilon is 120 and sigma is equal to this. We have to be very careful with these initial guesses. Then we use curve fit with our model function, our R data and V data, initial guesses, and we can extract them. And we get, like before, the model. So this is the data actually obtained from the true model that we fit for. And we can look at the data next to the model that we obtained, like this. And of course, as always, in these models, the most important things usually are getting sigma and epsilon, actually looking at the parameters. So I get sigma and epsilon, and this really tells me something about this particular potential. So it might tell me something about the physical system between these two atoms, and that's what's really important here. I hope you enjoyed this video. If you want more Python tutorials, I put together a playlist. There'll be a link to that in the description. Be sure to join the Discord server as well. We're almost at 500 members now, so that's really exciting. Anyways, I'll see you next time.